The Fourier decomposition is probably part of every analysis pipeline in one way or the other. It is used in frequency filtering of the data. And it is definitely used when you're looking at your data in the frequency domain. So let's have a look at what this is about. So it uses some properties of sine and cosines in order that help us to decompose our signal into periodic signals at different frequencies. So first of all, at a given frequency, a sine and cosine curves are orthogonal to each other. So if you multiply them, imagine them they are as vectors here, also as an integral. If you multiply these vectors for the two different functions, then they will that will end up as zero. So that means they are orthogonal. But also important to realize that there are these two orthogonal functions at one particular frequency. So it's the same frequency, but just with a different phase here. And also, if you have signals at different frequencies, for example, if at integer frequency intervals, then they are orthogonal to each other. So you can maybe see that. So when the lower frequency here has 1/2 cycle, the other one has a full cycle. So if you multiply these two signals with each other, you also end up with 0. So these signals are also orthogonal to each other. And orthogonal signals are very convenient if you want to decompose, or if you want to use them as basis functions to decompose a signal. You don't have to worry about any correlations between your basis functions. And in this case, they also have a clear meaning, namely, they are signals with a different periodicity at different frequencies. And at every frequency, again, you have these two functions that with a well-defined phase difference, sine and cosine waves. So I think we have a nice set of orthogonal basis functions here that can help us to decompose our signal and hopefully tell us something about our signal that we didn't know before. But before we go into the basics of the Fourier transform, just let's remind ourselves of the so-called Nyquist Theorem. I think I mentioned that already in another session where we talked about frequency filtering of our data. Because we usually sample our data with a certain finite sample frequency. I mean, our MEG data are usually sampled at 1000 hertz. Some EEG data are sampled maybe with 100, 250 hertz, something like that. And the number of samples determines how much information there is in our data to estimate basis functions of any kind. So you need a certain degree of, or a certain number of samples in order to estimate certain number of parameters in your data. And that's basically what we are doing here with our basis functions. So that also means that downsampling can lead to aliasing if we are not properly filtering our data. So if we leave too many frequencies, let's say, in our data, and after downsampling, we simply don't have enough information in our data to actually estimate all these frequencies independently from each other, this can lead to aliasing. So we talked about that in a separate session. I'm not going to explain it in much more detail again. So the rule is that you should filter your data at least below half of the sampling frequency. So if we sample our data at 1000 hertz, we should at least filter at 500 hertz. So low pass filter of 500 hertz would be appropriate. This is only the theoretical limit. So usually we go for about, to take into account other more real life limitations, we would usually go for something like a third, let's say 330 hertz. If you acquired your EEG data at 100 hertz, then you should probably filter your data with a 30 hertz low pass filter. And this is the Nyquist theorem, just in case you come across that term. And it's also related, as I explained in the previous lecture, to the fact that sometimes you see these strange, implausibly rotating wheels of cars in movies. Okay, so now let's put all of this together. So we know that we have our orthogonal basis functions. Basis functions at different frequencies are orthogonal, and at every frequency we have two orthogonal basis functions, namely sine and cosine functions. And what have we got? Well, we usually have a signal that contains n sample points. Let's say, depending on our sampling frequencies and the length of our signal, there can be more or fewer of these sample points. Let's say we've sampled our data at 1000 hertz, and we have a 1 minute recording, then we have 60,000 samples. And now you want to know which frequencies contribute to your signal and also by how much. So some frequencies may be more strongly represented, other less strongly. So what can we do? I mean, first of all, in other words, we can describe the problem differently. So you want to describe your signal as a linear combination of sines and cosines. So that's another way of saying we want to use these sines and cosines at different frequencies as basis functions. And yeah, that makes these sines and cosines actually ideal because they are orthogonal already, so we don't have to care about any correlations between them. We have our n samples, so that means we can estimate at most in n independent parameters. And we know that we cannot estimate frequencies above half of the sampling frequency anyway. So, and that restricts now the number of frequencies and also the frequency range that we can estimate. And we also know that for any given frequency, we actually have to sacrifice 2 degrees of freedom. So we have sine and a cosine that are orthogonal to each other and therefore provide independent information. So that means we actually have 2 basis functions per frequency. So now we can use that in order to apply the Fourier transform. So with all this knowledge that we've just accumulated over the last few slides, we can say that we can divide the frequency range in our data from 0 to half of our sampling frequency, and we can evenly divide that into n½ frequencies. So the frequency range is given by the Nyquist theorem. It's simply just the frequencies that we can actually determine from our data. And because we have 2 independent parameters per frequency, so we divide this frequency range up into n divided by 2 frequencies. So at every frequency, we create a sine and a cosine, and we use, for all of these frequencies, times 2, we use then the corresponding sine and cosine curves as our basis functions. And then we can fit these to our data, also project these to our data. Again, because they're orthogonal, we don't have to care that much about we don't have to care at all about correlations between them. If we do that, we get different amplitudes for the individual basis functions. Some might contribute a lot to our data, some not so much. And these amplitudes are basically our frequency spectrum. And this is the basics. These are the basics of the Fourier transform, and the fast Fourier transform is basically just a fast algorithm to do this. And the details are not really important to us here. So I'm cheating a little bit. I made some assumptions here, but I think this gives you an idea of what we are doing when we are applying the Fourier transform to our data. And in pictures, I mean, this is what we are trying to achieve. So first of all, I mean, I'm putting this here as Fourier decomposition. You can also call it the Fourier composition, if you like. So if you put different sine and cosine functions, on top of each other, you can create, in principle, almost arbitrary signals. I mean, but usually we want to do it the other way around. So we have a signal, let's say a step function here, and we want to approximate that with a certain number of sine and cosine functions. Then we maybe can just pick one, which comes at least somewhat close to the step function, so a sine curve with a corresponding frequency. But if we then want to improve the fit a little bit, we can add higher terms, 4 terms, 16 terms, and we will get closer and closer. I mean, we will not get absolutely, with a finite set of sine and cosines, I mean, in the case of a step function, we will then never get the, in terms of more realistic signals in theory or principle, you might get very close, but there's not really the point here. So you can at least approximate the signal with a certain number of sine and cosine waves. So this is what's happening here. This just illustrates it for a slightly more realistic case. So imagine you have your wiggly ERP curves. You will then fit your different sines and cosines, basis functions to these data and see how much they contribute. In this case, you actually see every frequency twice. This takes into account also the phase difference. So at every frequency, you can have a sine and a cosine. And then when you have your amplitudes, you plot them for every frequency, and that gives you the frequency spectrum. And it's often usually called the power spectrum. So every frequency only appears once here, even though I've just told you that it appears twice here. And that's because we usually don't care that much about the sine and the cosine part at every frequency separately. We are just interested in the overall power at every frequency. But in some analyses that might differ. But that's not something I'm going to talk about here. But this is how the power spectral density, for example, the power spectrum, is determined. Okay, I actually would like to leave it there. I mean, I don't want to explain the basics of Fourier transform in more detail at this point. There are nice tutorials, of course, that explain that more using a particular software like MNE-Python. I just want to give examples where this is actually used, not just as a pre-processing tool, but it's actually used in practice. So even with a relatively simple method like Fourier transform, you can already do quite interesting things. And most of you may have heard about the steady state response or steady state responses in EEG and MEG. If you present a periodic stimulus to your participant, then maybe not surprisingly, you also get a periodic brain response. That is, for example, the case in the auditory domain. So imagine you have a tone at a particular frequency, and then you modulate that with a carrier frequency. That means it more goes like woo, 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 woo. Then you will see this carrier frequency represented in your brain response. I mean, if you are in a at least reasonable frequency range. And this is illustrated here for different carrier frequencies. So here in these curves, I mean, I hope you can see that. I mean, you can see a high frequency here, which you usually don't see in the EEG or MEG response. There is something called the frequency following response, but you really need specific EEG devices. I think this actually comes somewhere from, I don't know, I mean, even from the auditory nerve or something like that. So this is something we wouldn't see in a normal EEG, MEG experiment. But if you modulate that, so you can see this is modulated here, then this carrier frequency is somehow represented also in the ongoing EEG. And if you look at the frequency spectrum, and that is basically a Fourier transform here, then you can see that for an 80 hertz carrier frequency, you see the peak at 80 hertz, 40 hertz, and at some lower frequencies, you can also clearly see here that there are also harmonics. So you don't just get this one particular peak at the carrier frequency, but also at multiples of that frequency. In the case of 10 hertz, for example, you know, at every 10 hertz here, something in between, which I'm not exactly sure what this is about. But the fact that you get these harmonics means that the brain doesn't just respond linearly to this input. So it does something else to the signal, which produces these harmonics. And that's potentially interesting to some people. And this also exists in the visual domain, the visual steady state response, very much the same. In this case, you just present some visual stimulus with a particular frequency, and then you see this frequency in the frequency spectrum. So here, this is sort of the idealized case. This is the stimulus with a sharp frequency in the spectrum. If you look at the brain response, low frequency, higher frequency, you can see that the brain responds in a periodic fashion, but it doesn't just multiply the input. I mean, there's some nonlinear process at work here, which means that you have some more some harmonics in your signal as well. And then you can analyze these data or use this paradigm to your heart's content and look at how this differs between different participant groups. And you can do also more interesting things with it. So that's what I just briefly want to highlight here. Also shameless self-advertising here, because I'm using one of our own studies. Because not only do you get a periodic response if you present the stimulus periodically, so here natural images of objects were presented at a frequency of 6 hertz. So then you expect a response at 6 hertz in the brain, just as we just saw. But you can also intersperse a particular category of object. In this case, every 5th image was a face among other objects and animals. So basically, faces were presented at a frequency of 1.2 hertz. And if the brain distinguishes or can discriminate between these objects here and faces, then you should get a face discrimination response at 1.2 hertz in the brain. This should be specific to the discrimination of faces from other objects. So other confounds are very unlikely to produce a peak at 1.2 hertz. It's a very reliable, or it should be quite a reliable brain response, because this peak in the frequency spectrum is basically an average across everything that happens over time that distinguishes faces and and the other objects over time at different stages of the evoked response. So it's all summed up in one frequency response. So you might actually get a nice response at the frequency of 1.2 hertz, even after just a short amount of recording time. And that's exactly what has been reported. I mean, obviously already a while ago. So Bruno Rossion pioneered this paradigm. So we did this here with EEG and MEG combined. And if you do this, then we clearly see, first of all, clear responses at 6 hertz. That's not surprising. That's the visual steady state response, in this case, to pictures of objects. But we also see clear responses here at 1.2 hertz and harmonics. And this is the phase discrimination response. So that's specific to the discrimination between phases and objects. And that's here in the EEG. So these are just the channels that are plotted here. So right lateralized in the back. And also in gradiometers. And now you can sum across harmonics to increase your signal-to-noise ratio, and then you can analyze them in whatever way you want. But we also then subtracted them to source estimation, so you can do everything that you can do with other brain responses, with EEG and MEG brain responses. So in this case, we use source estimation. So this was just really a very quick overview of what the Fourier transform is, frequency decomposition. And it is very commonly used to filter data to different frequency bands, look at the frequency spectrum. And I hope I could also show you that this already leads to some potentially interesting analyses. Yes, and more about, for example, the time frequency decomposition in other sessions.